So the last three classes we have will be talking about basically this transformation of you stand in a field, you know that some of these water wells to your left have dosages of some dissolved components which are above drinking water standards, and you want to know exactly what you're going to do with it. And so you need to be able to frame an assignment, much like the ones that you've already been given, where you have Smithville, you know there is a site, which is a field, but before you measure something in some wells that are there and investigate to see exactly where the source of the plume might be and what the stratigraphy and characteristics of the subsurface might be in terms of not only the distribution of those beds, how extensive they are and what the architecture looks like, but things like permeability, sorption characteristics, flow velocities, distributions of contaminants in the plume. That's all the stuff that you want to be able to pull together. And so if you're standing on a featureless field with no idea of what's underneath your feet, that's the position that you come into this. And so what we'll talk about in these three periods is how you turn it from no knowledge at all whatsoever into being able to define exactly what's present in situ. And we'll talk about direct and indirect methods of investigation. They're preceded maybe by knowledge that you can get from what other people have applied at that site. But direct investigation would be digging trial pits, drilling holes in soil and drilling holes in rock, and maybe sampling. That gives you some point information about what's below you. And then being able to link that together by something that looks at something larger than a core, which is the size of your fist. It might be 100 meters long or 1,000 meters long in some cases, but something that only represents a very small part of your aquifer or subsurface, or aquiclude for that matter. And being able to say what happens on the size of your site, which might be, if it's Rutgers Neast on the Bennis Pike, it might be 100 meters by 100 meters. Some of the plumes that we showed where we're talking about retardation factors and how dilute a small 0.4 barrel of TCE might become how large, then that's the size that your site investigation might have to go to. And so we'll talk about the methods that we'd be using for that. And today we'll talk about drilling. So in other words, being able to get that information directly. Maybe retrieve samples that you can do some tests with it. If you need to do tests, we've already ascertained, I guess, that it's not very helpful to do tests on samples for dispersivity because that's a function of the entire aquifer, not just a point measurement. And so we might think about doing that. So there's a bit of verbiage on what to do. We want to figure out the parameters we need to know. What do the bedding look like? Which one's a high permeability? Which one's a low permeability? Where is the source? Where that might travel? And what might be the characteristics that define how quickly that material might be traveling downstream? And so this is exactly the kind of problem we're trying to find out about. And so this is you're aware of this. You worked with Smithville for a little while. And so this was discovered because people had drinking water from groundwater that turned out to have some concentrations dissolved in it. And so that means that you find that somewhere, you look upstream from that. To do that, you can't do that just by looking at the site. You need a borehole. I suppose if you had some wells that are drinking water wells and you had steady state elevations in those, you could put together a contour map of the hydraulic water table and project that upstream from where your measurements might be to figure out on which trajectory that problem might exist. So that would be one thing that you might do. But really what the initial stages would be, desk study is a good enough name for it as anything. Get anything on the site that you can to be able to explain what might be there. So certainly in Pennsylvania, there'd be Pennsylvania Geological Survey reports on hydrogeology in certain areas of the state. They might be too broad to be of use, but there might be some specific information on the site. Someone might have done a site investigation to be able to vet that site before it was up for sale, so you don't buy a site which has a liability attached to it already. Some of those reports might or might not be confidential, but you can imagine that you might be able to gather anything that would be relevant from library or digital records that are available. You can take, with Google Earth, you can take aerial photographs or have aerial photographs available. Again, they only tell you something about the geology, not anything very specific, but it might give you some information about where you might look and drill holes. For instance, it might locate where there were springs that were seeping and you could sample and get some information from that. And field mapping would be walkovers. And so I guess it's not here. Where's the site? I guess there's a different figure that I want to use. And I guess to make the point of what the site investigation is, and that's where we'll end up. I thought, yeah, okay. I thought I had a nice figure of a site with a well bore in it, and looking at the size of the sample that might exist in that site relative to the total site size. And I don't see it here. So, okay, I guess I should have been more careful when I looked at that this morning. So the point is that if you take a sample for site core, might be a couple of inches in diameter, might go down 100 meters, but that is information just along that single line. And so if you want to expand that and get it for the volume of your site, what you can do in addition to drilling is to do things with indirect investigations. So indirect measurements are just taking a parameter which is a proxy for something you might want to do, and that proxy would be, in using seismic methods, the proxy would be the seismic velocity of the ground, the acoustic velocity. So in other words, instead of being 600 miles an hour that I'm talking to you at, rock velocities would be a kilometer per second to a couple of kilometers per second. And so sometimes if different units have different seismic velocities, then you can pick up from the interface between those two different materials. You can use geological prospecting to pick up that. So we'll talk about that, I think, in a week today. The idea is that you can put geophones out on the surface. These are just seismometers that are a weight inside a cage, an electrical cage. When the weight swings, because you're exciting the outside of the housing, then it puts up an electrical current in the surrounding coil, and that's recorded as basically what you'd think of as a seismometer trace. So this would be displacement versus time. An earthquake comes, and all of a sudden you get a seismic wave which damps out over time. So this gives you a first arrival, the time when it arrives from being shot off. This shot might be a sledgehammer with an electric cable on it to close a circuit, or it could be a stick of dynamite. But what it does is it puts seismic waves into the ground, and they will travel either by going down to the fastest layer, going across and then up through a slow layer, or you can do it by reflection. So they'll either refract or they'll reflect. And so you can imagine that you'd use this to be able to say something about the stratigraphy of each of these layers. How thick are they? And it'd be the same as you get out if you drilled a well or drilled a borehole and took samples all along that length, because you'd have core that represents these interfaces. So it's just another way of doing it. This gives you great detail at a single point because you get a sample back or you get drill cuttings. This gives you a little detail inferred over a very large volume of your site, either by refraction or by reflection. And so that's the idea of doing that. So the idea is to define the stratigraphy. The other method that's used is the same as you'd see on these archaeology shows, like Time Machine, using GPR, ground penetrating radar. So the idea is you have a transmitter. They're usually a single unit these days, not two units that are separated. But you move on the surface, there's a radar wave that comes out of a transmitter, and in the same unit it picks up the reflected wave. Again, a two-way travel time as it goes across here gives you the depth of these layers. And maybe you can say something about the dielectric constant that controls this. Not important for us to know now. And again, this is just another substitute for a borehole, which would give you core recovered to the surface, which would say exactly where these interfaces are. And so that's, I guess, what we'll talk about today. And not about geophysics, but in terms of direct methods. So this wasn't the one I was thinking of, but this says exactly what I wanted to say. So boreholes are essentially a 1D sample, usually vertical, but not always. Sometimes they're inclined, which gives you information of what's present here. You'd like to know what the stratigraphy is, typically, and so they will let you know exactly where these interfaces are, either by changes in drilling rates as you go across this boundary, or by the samples that you take out of this, either by taking core or by collecting the cuttings that get forced up on the drill. If you drill a trench with a backhoe and get into it, at risking your life if it collapses, of course, then you also get some idea of the stratigraphy, but at relatively shallow depths, talking 6 feet, I would think, for this. And probably, I think, you probably shouldn't do that because of OSHA type rules, because the trench can collapse on you. And if you want to see what a 3D picture is, of course, if you excavate the whole site, you don't have a site to worry about. So perhaps problem solved, but you can rarely afford to do that. And so the way that you get information about the 3D distribution of these interfaces, if you like, would be by geophysics that we just talked about. Very quick to take a GPR machine over the surface of a field backwards and forwards and get a full 3D picture of it, and likewise for seismic as well. So those are the essence of the methods. But if we're doing drilling, then the big division is whether we're going through soil, which is obviously shallow, or rock. And the techniques that are used are different depending on that. Typically, to get to rock, you have to go through soil. And so you'd have to start off with a technique that allows you to get down to the bedrock and then continue on with a different technique, perhaps. And so the three main methods, which you might see if you're working as an entry-level engineer in these sites, the first job you'd go out to would be in soil, by augering. And so augering, the idea is that you drive a corkscrew into the ground. Typically, you drive it by turning it, but it will rotate faster than it would do if you just screwed it into the ground as a screw. And so by turning faster than that natural progression, it will migrate the cuttings up the auger flights up to the ground surface, and you can sample them there, you can bag them, and there's only a small delay between when it starts at the base and works its way up to the surface. So you can use a so-called solid stem auger, which would just be screwed into the ground, and we'll look at some of these things later on today, and it would bring the material up on the flights. It would leave a hole, not a very stable hole, after it's gone down to depth, and then you just pull out the auger flights. The other option is to have an auger, which is a so-called hollow stem auger, and that would be a pipe with these flights on it, a central piece of drill steel in the middle, and a cutter head, and you screw it down into the ground, and then when you get to a particular depth that you want to see what's going on, you pull out this solid stem and the cutting head, and you can take samples below it up to the surface and see exactly what there is in the subsurface. You can tell from when you go through different materials, from clay to sand, etc., the penetration rate will change. It'll either be easier or less easy to go down, and you can make inferences, because as you add these stems, you know exactly what depth the tip is at, and therefore you know that if it's changing from one material to another because it's making strange noises, then you know what that depth is just by counting up the number of flights, each of which might be 3 feet long or 5 feet long, whatever they are in that particular case. So we'll look at that in a bit of detail. So soil only for this. Drillers will not like it if you want to keep on drilling into the weathered bedrock which exists under the soil. Air flush or water flush rotary drilling is a common technique. It's just a piece of drill pipe which is hollow. It has a head, a cutting head at the base. It's rotated and pushed into the ground. It breaks up the material underneath the impact, not really impact, but the pressure of these heads just fracture off little button-like pieces of rock at the bottom. Flushing water or air, it could be air or mist as a foam, or it could be water, or it could be water and drilling mud. And this is to be able to take the cuttings from here and bring them up to the surface, where you can hopefully not catch them in the head if it's air flush, or just sift them out of a collector tank to be able to see exactly what the material is. You know you have certain lengths of drill steel down from the surface, so you know which depth you are. And so these samples that come up, you can either bag and recognize in terms of what the material is to see what the stratigraphy might be that you've gone through. So again, to build up a picture of exactly what the subsurface looks like and what the depths of these different layers are. Importantly, I guess you don't get a full sample. You get drill cuttings, which would be, nail-sized pieces of rock thrown at you if it's an air that's flushing this, or gathered in the drill mud that returns with a kitchen sieve, domestic sieve, to be able to take them out of the water. So this is for soil and rock. And I'm not sure what I missed, doesn't really matter. Yes, soil, yeah. No sample recovered, I guess that's the one take home. And then there is rotary drilling. Some rotary drilling, sometimes also called diamond drilling, not drilling for diamonds. But the idea is that this is just a tube. So this is just a cross section through it. It's a tube that has on the tip industrial diamonds around the rim of this. And this, rather than being turned and pushed hard into the ground, as is the case here, to break off little pieces as it doesn't impact them, but as these cutters roll over the rock at the bottom of the well bore, this actually abrades the rock. So it's like a cookie cutter, not pushed in, but it is rotated. And as it rotates, it abrades the material ahead of these cutters. And as a result, the core just moves up into the core barrel. So as this assembly moves down, then it leaves the rock that it's cutting around to rise inside the drill steel. When you get to some depth, you break this off and you bring it up to the surface. And when you bring it up to the surface, you have this sample that's in here that you can then take and put into a core box. Geologist or an engineer can look at it to see what it is. You can look at the fractures in it because you know those fractures are the things that water is going to be traveling in. You might look at staining on those fractures to see if water is actively traveling in it. And it would give you a demarcation again between different stratigraphy that's present in situ. And this is really for rock only. So those three things. Augering for soil only. Rotary drilling for soil and rock, and diamond drilling for rock only. So this is perhaps, I don't know whether these are better pictures or the same. Typical methods, cable tools. This is the Drake well, first well discovering oil in Pennsylvania. They used that with a cable tool. So all it is a big heavy weight. You lift it up, you drop it, it breaks off stuff here, and then you go in and bail it out. Just take out the slurry, take it up to the surface, and then reintroduce this cable tool. Keep on dropping it for a few times to break off enough that you can then recover. Very, very slow and not used very much, but it is used some places. Rotary drilling is this. This is this tricone bit at the toe. I guess this is what made Howard Hughes famous, or rich rather, not famous, perhaps both, by inventing the tricone bit for drilling. So this, I don't know, how deep is the Drake well? Does anyone know? I'm guessing it's 60 feet or something like that. So 20 meters, not very deep. And so that would be, deeper things would be inaccessible with this, but would be accessible with rotary drilling. And so this would be for rock and soil. Cable tool is also for rock and soil. Augers here are just for soil. So this is basically the sequence. So you have an auger. It's a single piece of solid 1-inch diameter steel. Comes in sections, maybe 3 feet or 5 feet long. They have a female hex nut at the top, a male hex nut at the bottom. One new tube goes into the other, gets a pin across it to hold them static, and you just turn it. You turn it with a table on a drilling rig, typically a truck that arrives on site, and as it goes down, this cutting head cuts a new portion below it. It raises up the removed material up to the surface. You sample it here. When you get to a point where you might want to, you can sample just the sludge that comes up on the flights here and bag it. If you want to get a pristine sample ahead of the auger, then you pull rod and then you introduce into the bottom of this some kind of sampling device. We'll talk about sampling devices on Tuesday. They come in 2 flavors. If you want to sample sand, something that is not cohesive, it falls apart and is friable, then it's called a split spoon. It's basically 2 pieces of tube, 18 inches long. They open, they have a cutting shoe at the base and a coupling onto drill steel up to the top, and you put it down to the bottom of your drill hole, and then you physically bang it into the ground with a monkey, it's called a monkey hammer, and it goes in. It takes a sample of the material that would have been here. And then when you pull this out of the hole, it recovers it to the surface. You break it off the end. You take the cutting shoe off. You take the disturbed sample out. And you also use the number of counts, blow counts it takes to go 1 foot as a measure of how dense the soil is. Relative density it's called. And then once you've done that, you pull this out and you put the auger in, add another length to it, and just keep on going. And you decide when you want to take it out to get a sample if you want to use that. The problem with that is, as on the right-hand side, if you go through material which is silts and sands, which have water in it, as soon as you pull this auger out, there's nothing keeping the hole open. There's nothing in it other than water that might flow into it from the sides. You're not adding water to it. And so this might slough into the hole. And so if it sloughs into the hole, then when you take a sample, the top part of your sample you have to be careful of, because it might not be pristine material at that depth. It might be reflecting the material that's a foot above it, or 10 feet above it, or 20 feet above it, whatever. And so one way to get around that is to use a hollow stem auger. And the hollow stem auger is this. And so it's like a solid stem auger, but it's hollow. And so it has an outer casing, which is this, which has these auger flights welded onto it in a spiral. And it has a central piece of drill pipe, which goes all the way up to the surface also. And at the end of this drill pipe, there's a cutting head, little 2 prongs that are angled. So when it turns, this head actually cuts the advance and allows it to go down piece by piece and remove this. The stuff that's cut here ends up going up on the flights like this, on the outside, of course, all the way up to the top. You can sample it at the surface if you wish, but the whole idea of this arrangement is that now when you're down at depth, what you can do is you can pull out this central stem, solid stem. It comes along with this cutting shoe, and it leaves the bottom of the hole open. So this is epitomized here. So you go down to the depth you want to be, you take out this stem, and it's left with an open void. This is casing that's protecting it from falling in. And then you enter some kind of sampling tool down it. If it's a split spoon, like we said before, you bang this a foot into the material ahead of the borehole, take out your sample. You're absolutely guaranteed that this isn't the problem you have, right? You're guaranteed that this can't happen because you have a casing on the outside that protects against that. So that's it. So quite a straightforward thing. So augers, solid stem and hollow stem, much better because you get samples from it, but slower. For rock and soil, so this is only for soil. For rock and soil, we can talk about tricone or rotary drilling. So here is this thing with the tricone bit, 3 rotating. They don't actually rotate themselves, but they rotate under the motion in the bottom of the hole. Typically, well, not typically, you can drill maybe with air flush. You have to flush a fluid down the center of the drill stem. It takes the cuttings that are developed here and brings it up in the annulus between the drill steel and the side of the hole. So that's why you need something to flush the cuttings out. It might be air flush that you can work with, but more usually it's water or it's drilling mud. And so the drilling mud actually provides a pressure to support the hole and stop it from collapsing. And you know how to calculate that pressure, right? Rho GH, which is this. And so this just acts as the pressure of the water keeping this open. And when you get to some depths that you want to, you pull out this drill stem, you replace it with drill steel with a sample on the bottom, bang it into the ground, or push it in. I guess you'd bang it into the ground if it's very strong soil, and then take it out and then continue with another things. That has exactly the same problem as the solid stem auger, is that when you pull the drilling bit out of the hole, you potentially allow the hole to collapse. And if you then take a sample, the top part of your sample might actually be not from this depth here, but from this depth here. And so that's the trials and tribulations, I guess, of using that. So we talked about augers for soil, rotary drilling for soil and rock, and diamond drilling for rock. And so this is basically the idea of diamond drilling. These two are similar, but the idea here is it's diamond drilling because on this shoe you have industrial diamonds all around the circumference of it. And unlike tricone drilling, most of the action is done by putting a heavy weight on the drill bit and turning it, but not abrading it, just breaking off little pieces that can be washed up in the top, and then you can sample ahead of it with some tool like this. In diamond drilling, the whole effort is to be able to actually recover an intact sample of the core by making it abrade all the rock in a tunnel around the cylinder that goes down. The core rises up inside the core holder. Again, just like tricone drilling, there's a drilling fluid which is circulated down through the system, takes the cuttings away from the drill bit. But these cuttings, instead of being little chips the size of your finger nail, would be flour, because it's abrading it. It's basically rubbing it away. And so these would be the grain size of the material that you're cutting into. And then the fluid that hits it at this point brings these cuttings, rock flour, up to the surface. Typically you don't collect them because they're no use, they're just flour, and you're counting on the fact that you get some good quality core here. Usually there are fractures in the core, so you don't get an intact piece of core which is 2 meters long or 3 meters long that hasn't broken here and maybe rotated against itself in the core holder. And so this here, I guess this would be the side of the borehole that you're making, all the way down here. And so this return fluid would be coming up inside the borehole. between the borehole and the drill steel. Right? If you want to get more sophisticated, then you can use, this would be, I guess, called a single barrel core holder. And the double barrel core holder. And so here you see that the water comes down, it touches the core that you've just drilled as pristine core, and then it circulates around it, then it returns on the outside. A double barrel core barrel has a sleeve. So this here is an inner sleeve of steel, right here. The water comes down outside that sleeve, so it doesn't touch whatever is in here. It only touches the rock at exactly this point where it comes against the cutting shoe. Cutting shoe is the same, and then it goes up on the inside of the borehole. And so these two red lines are again the inside of the borehole. So in this case, you might be interested in the fluids you have here, and you might not want the core to be contaminated with the drilling mud that you're putting down here. So that's an obvious reason why you want to do that. Perhaps a more important reason is that this sleeve that we have on both sides, one allows you to separate the core from this drilling fluid, except just at the tip. But also, what you can do is you can use a wire line to sample this. And so the idea here is that the drilling fluid is coming down here, it's diverted around the inner core holder, so it doesn't touch it. But when you get down to the depth where the core has risen up completely within the core barrel, you know how long your core barrel is, 6 feet, so you know you can advance 6 feet beyond the bottom of the hole when you're drilling. You can measure that on the surface by how much new rod that you add at the surface and push down. But you can fish for this, you can grab onto this, and you can pull this whole assembly up to the surface. So you can pull this, the whole assembly would be this thing here, containing the core. So this thing would come up inside the drill steel, and you sample it, and then pull out the core, and put it in core boxes, and do a description of it, and log it to be able to see exactly what you've done. So these things are saying exactly the same things that I've mentioned as we've gone through that, so I won't go through those again. It comes from an EPA manual, which is actually one of the things on the drilling, on the syllabus. And this is another table that actually makes the case for what these things are. So we've talked about augers, hollow stem and solid stem. We've talked about this wouldn't have drilling fluid. We talked about whether a casing advances. Of course, the casing is the hollow stem in this particular case. Talked about what the material is that you can get through, what kind of depths you can get to, 150 feet, sounds about right. Borehole sizes in inches, 22 inches sounds very abnormal. 5 or 12 inches sounds more normal to me. Yeah, that sounds very big. Whether you can obtain samples, I'm not sure what the notation is for S and F, soil, rock, and fluid, I guess. So yeah, so samples of soil or rock speak for themselves. Fluids would be whether you can get the in situ fluids recovered. So if you're drilling into a clay, then just by taking a solid sample of the clay soil, you'd by de facto also recover the fluids that's in that. Whether you can core, I guess you can core with solid stem auger if you use it to initiate the hole and then core beyond it. Otherwise, I don't think that's right. It's come from a book, so I don't know this. So the things that we've talked about so far, hand auger would be the same as a solid stem auger, just that you're screwing it into the ground. People use those sampling wetlands and things. Fluid rotary, air rotary is just the different drilling fluid. Much easier to use because you don't have to supply water, which might be lost to the formation, and therefore you have to have a new supply of water to push underground. Hammer drill is just banging by percussion at the surface and having that driven into soil and soft rock. Yeah, fine. So cable tool, Drake's well, etc. So there's lots of these different things. Anyway, so that's it. Let's look at some of these things. Spend time just doing that. So always dangerous to share your own photos album with people. You never know what you might have in there. Yeah, don't worry, I sanitized it. I don't want to disturb you. So, not a site investigation drill. These are called air tracks. They're usually for drilling blast holes in mines. This is a mine in western Alberta. Go due west of Edmonton, 4 hours, you hit the Rocky Mountains, Canadian Rockies. And this is just hooked to a compressor, has an air line going into it, has a solid piece of steel, and the air line at the top is just like a jackhammer. Airline pushes against it, the hammer goes down, makes a void, the air rushes out, the hammer jumps back again, new pressure, just boom, 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 about the same thing. And so it will make holes which are probably a few inches in diameter, and there you can add multiple lengths of steel to this to go down 20, 30, 40, 50 feet, I would imagine. And then typically for these, you don't take samples, you don't log the chips that come out, because all you're interested in doing here is making a hole which you'll then put ANFO, ammonium nitrate fuel oil, mixture in as explosive, put a detonator in it, put stemming at the top to keep the generated airs locked in, and use it for blasting a bench in a open pit mine. Not a very good picture. A drill, so it's a petroleum rig, again somewhere in the foothills of the Rockies in Alberta. And so this is a full-scale drill rig. They come in on trucks. There might be a truck base here somewhere, but I can't see it. It's too dark. For scale, I don't know, this is 50 feet in the air. One story is of a house. One story house is 10 feet, right? So that's about 50 feet. Pulled on site, stays there, runs 24 hours a day to get down to some depth where you hydraulically fracture it and bring out either oil or gas out of a deep reservoir. So not the drilling that we're talking about here. That's what it looks like when it's torn down. Yeah, that's also in Alberta, but not the same rig. Not the rigs we need here either. These are blast hole rigs. So this is a coal mine, again, in western Alberta, close to in the foothills of the Rocky Mountains. These are just putting down holes as quickly as possible. I'm guessing they don't add another length of steel. They just go down the length of this set, which might be 30 feet. Those are used for blasting. They're filled with explosives, and they would make benches that would be left as they are here. Again, not another rig we'll look at, but this is a clean-out rig in Norman Wells in Northwest Territories. And this one is just actually cleaning out the wellbore, but close to a petroleum rig. So we'll look at some diamond drilling rigs. So I bring this up because this is in the Caribbean. In the island of Montserrat, which erupted volcanically from 1996 to about 2014, I think. Where's Hispaniola?
Puerto Rico's right there.
Yeah, that's Puerto Rico. Where's Santa Dominica? Where's Santa Dominica, Dominican Republic?
No.
Further left?
Yeah. Right there.
Hispaniola, yeah, Haiti in the middle. Covered with trees, not covered with trees, as I recall. So yeah, so Montserrat in the Caribbean. And so what this was it started erupting in 1996, wiped Soufriere Hills volcano right here. It completely wiped out the town of Plymouth. 10,000 people living on the island. It's a kind of a UK protectorate, so 8,000 of them went to live in London, 2,000 stayed. The whole southern part of it became an exclusion zone. Everyone lived in the north, so quite a traumatic event, really. It's kind of strange. The people who lived there hated the volcanoes going off. The people who came as scientists to look at it liked the fact that it was doing that. So this is a volcano in the background, Soufriere Hills volcano. This was the town of Plymouth. This was a clock tower. that must have been 20 feet tall, I would guess. These reworked deposits, blocks and ash, are all ash that's been washed down here as so-called lahars, just reworked volcanic sediments that are placed there. So this is probably 2000, so six years after the beginning of the eruption. The whole of Plymouth was evacuated. Yeah, this is it's kind of sad for the population. And so as part of this, there was a project to look at kind of the plumbing system of this volcano. And so the idea was, actually to go back, I guess these are all, the idea was to think of this, why is it done that? I'm going the wrong way. So the idea was that if you wanted to look at the magma chamber underneath this, you'd imagine that it would be somewhere underneath the peak of the volcano. And so this project was to drill some holes away from the volcano on a traverse and to instrument them. There are 200-meter holes, and at the bottom of the hole is a seismometer, and there was a strain meter that would pick up very subtle changes in stressing of the borehole, and there was a tilt meter. And so tilt meters are developed actually by the company that was developed by Chris Wright, who's now the Secretary of Energy in the current administration. He built a whole company out of this, Liberty something, who developed this technique to be able to put tilt meters in the ground. So you drill a hole maybe 3 feet deep. You'd put this long, slim, 4-inch diameter tube in it in the bottom. This thing would have a little, like a spirit level in it, which had mercury in it, and it could predict or measure electronically the tilt of this meter in the borehole. And so you'd pack it back with sand around it so it was held in the hole because you want to retrieve it later. And then you'd hydraulically frack your site in the oil industry, in gas, and this would deflect. And you'd use that deflection to calculate the whole deflection over the surface, hundreds of meters away from the borehole, and be able to predict exactly where your hydraulic fracture was going. So that was the technology that was used there. So a strain meter, a tilt meter, and a seismometer. And so the idea was that if you have something like a magma chamber 5 kilometers underneath this hill or 12 kilometers deep, you can measure the displacements at these points if you have boreholes that one may be deep enough so it's not completely swamped by surface noise. So you get a very clean signal because it's 200 meters deep. And that the instruments are very precise. You can measure strains, changes in volume relative to some baseline of nanostrains. So 10 to the minus 9 meters per meter. So very small strains. So there were along a trajectory. So maybe this is 12 kilometers, of the order of 10 kilometers long, and there was a cross section of 4 of these strain meters along that section, all the way out to one that was close to the jail, and which is no longer existing. So I'll go here. So what else? Why won't this go? Just did this before. Back here. So this is one of the drill sites on the eastern side of the island, placed actually the site of the old airport, which is completely wiped out by this eruption. The idea was that you need drilling water to do this. This was one stopgap measure to do this. This is a tank in which the drilling mud is mixed and then sent to the drill rig. And this is the drill rig. So this is a turntable. This is a drill pipe, hollow pipe that goes down into the ground. This is a turntable which provides the motive power to turn with the drilling shoe down the hole somewhere. This can be pulled down into the ground so you can push against the bit at the bottom of the hole. And this is a wire line up into the top of the mast, which is attached to drill steel here with a swivel attached to it, which will pull the drill steel out and put it up the mast. So that's exactly it here. This is a casing that goes into the ground. It doesn't want to get bigger. Does it get bigger on the screen? Yeah, I guess it does. So this is casing with a drill steel, smaller diameter going into it and then going into the ground. In this particular case, this is getting ready to be pulled out. These are the controls that control how quickly this goes down and how quickly it goes down on this stage, which allows it to push into the ground. Yeah, another close-up, something to stand on. You only need to do this once and you know exactly how to do it for the rest of your life. This is a drill shoe, cutting shoe. So this is drilling fluid would come down the inside, go out to the inside and go back up the hole on the outside. This drilling shoe is larger diameter than the pipe, obviously, so it doesn't get stuck in the hole. These are diamonds on the outside to be able to make the hole bigger than the pipe so it doesn't get stuck in the hole. These grooves allow the water to come down the inside and get pushed out. And these would be the diamonds, which you can't see very well on the cutting shoe. I don't know. Oops, no, you can't see them much better. Anyway. I guess this is another ring of industrial diamonds. So in the same way that you want to ream the hole larger than the casing or the drill pipe that's following behind it, you want to make sure that really is the case. So this actually also abrades it to make sure that the hole stays large enough to be able to not grab onto the drill steel behind it. And this is just pushed into the borehole. Okay. So this is something, yeah. So these are the individual pieces of steel that are screwed together. So you take them up into the mast. So this is a coupling that you screw into the drill steel. It has a coupling to a cable that goes up into the mast so that you can attach to the drill steel something to pull it up into the mast. You have to lift it up 10 feet to be able to orient it so you can screw it onto the drill steel that is actually in the hole, and then just keep on adding, going down 10 feet, adding another 10 feet by raising some up into the mast, screwing it on, and then going on. So you get a continuous pathway to the base of the hole, which might, in this case, it was only 200 meters, 600 feet, but it might be longer than that. And so this happens to be a very special lightweight drill that can be containered and transited around the world to scientific drilling sites in this particular case, but the same techniques as is used if you rented one in Pennsylvania. And so you add lengths of steel onto it. This is the casing, which is being applied here. The drill would go down, water would be, once it's coupled, drilling fluid would be pumped in here, it would go down to the bottom of the hole, it would come out, and it would return around this casing here. So it would come out here, and I think in this case they're just wasting the material, not regathering it and putting it back down. So that's a pretty simple technique. Close up, another close up of the same stuff. So this is actually, it's drilling with casing in this particular case, which isn't so usual. I'm moving ahead and not telling you, but we mentioned about the idea that what you'd like to do is not, once you're down at 200 meters, pull 20 10-meter pieces of pipe. They wouldn't be 10 meters, too tall to get in the mast. So once you're down with 15 pieces of connected rod in, you don't want to take those 15 out to be able to get a sample down the bottom and then put them back to advance to the next place again. So what you can use is use a wire line. So the wire line is this. So this is a core barrel. And you can imagine that the tubing that's doing the cutting is sitting. This is a central piece of tubing inside that. And it allows the core to go up in it as the whole assembly goes down. Yes, right. Do I have your attention for once? That's amazing. sure. Yeah, this is it. Yeah. So this is the. So this is this is the whole idea. So the wire line is actually this contraption here. It sits inside the main drill steel on the outside. It has a connection at the top that you can go fishing for it. And you go fishing for it by dropping a piece of cable down that attaches onto this conical piece at the top, grabs onto the side of it. You can imagine, I don't know, yeah, you can imagine a cone with something with the spring steel on it, just going around the cone, getting wider and wider as it goes around till it snaps on the bottom of it. And once it snaps on the bottom, you've got it. You can bring it up to the surface. And so in this particular picture here, this is exactly this. This goes inside the main core. It only exists, this is probably 20 feet long, I'm guessing, of that order. It only exists in the very bottom portion next to the cutting bit, which is right here. This is the bottom of the core barrel, which sits inside the cutting bit. These little pieces inside may or may not be pieces of spring steel. So in other words, like a comb that you comb your hair with, these pieces of steel are there to catch the core, let it progress one way, but not let it fall out of the bottom when you detach this thing and pull it up the hole. And so that's it. And this is the top of the core barrel. So the top of the core barrel, if you see it here, has a little cone with a collar around it that's recessed. And this is exactly what the clip on the wire line is going to attach onto. And then it's going to pull out this whole assembly. This is the core barrel at the bottom. These are swivels so it can turn and do stuff while it's drilling. And then this can be brought up to the surface. And that's exactly what they look like. So this is the little conical thing that this wire line attaches onto and brings it up the hole. Quite clever, really. Mud tanks to mix mud with bentonite. Bentonite is used to be able to make the water heavier because it takes on the density of the combined slurry, and it acts to better keep the hole open by putting a larger pressure against it if it's a larger density, larger unit weight. And also is better to be able to bring up the cuttings to the surface, because you know that when you try and move something with flowing water, the drag on that is proportional to the density of the fluid and the velocity squared, right? And what's the Euler number, in other words, from fluid mechanics. So this is, it gets taken to site in a container, shipping container. 30 feet and 60 feet, you get shipping containers, a regular shipping container you see on a container ship. And so it all pulls down and is reassembled on site. This is the same rig here. This is the mast. This is the turntable. This is the cable taking new pipe into the mast. It's on a connection here, which allows you to screw it into the threads on the top of the drill steel and then lift it into the mast by using the capstans that are here. Beautiful Caribbean. And that's what it looks like when it's broken down or when it's not put up. The mast here is separate. This rotates vertically and has a proto mast that this aluminum mast fits onto. It's aluminum, so it's light to travel, and the different connections that you have. This is the mast laid down. So this is the mast going into the page with the turntable right here that attaches onto this. Works off hydraulic takeoff, power takeoff using hydraulics. Manhandling drill steel into the mast. Can't see if this is a connection here that takes it into the mast. Going into the ground. 24-hour day drilling, actually, because it's there. There's nothing else, not much else to do except carouse, I guess, on the island. Nighttime drilling. So this is rotary drilling. So you come up with a sample, it comes to the surface. More rotary drilling. This is the mast, different kind of mast. These kinds of rigs were developed for exploration for things like minerals, nickel. They'd be used for exploration for critical minerals these days as well. So this is the mast which the drill steel gets brought up on. This is drilling at an angle. to be able to hit a particular site, location in the ground. This also is somewhere. This is in Sweden. So this was actually at the site of Sweden's low-level nuclear waste repository, which I think now is commissioned. And it's to be able to explore, to look at the groundwater behavior, to make sure that when you put something in the ground, it doesn't end up in Stockholm, basically, right? Picture. And so this is actually their low-level disposal site, a place called Forsmark in, how do I get back? In Sweden. So this is exactly that. This is just a housing so the people drilling don't get wet. This happens. This was in October of 2003, I think. This is the mast. This is coming towards you at an angle with the drill string here. This is the motor that's doing the turning and goes up and down the mast to be able to allow the drill steel to be abraded into the ground. This is a core shack, taking the core out of the core tubes. These might be core tubes here. This is actually core by the looks of it. These are core boxes, lots of little divots that you'll lay the core in and very carefully mark the depths so you can have information to be able to use at some future stage to be able to go and look at the core. And actually I don't see what, I can't see what that is. What's this at the bottom? Yeah, don't know. So it always does that. It always goes back to the native ones. Where are we? Yeah. So this core shack. Tons of core. Very nicely arranged. One of the nicest core shack I've seen. This, you recognize this? This is on the front of your. This is the. Isn't this the icon for the canvas thing? This is, let's see what the other ones are. I didn't look very closely at them. So this is a rotary drill as well. Rob Connors. This is in Norman Wells, Northwest Territories. If actually you've seen this site before, I think. It's quite cool that you can link the geography of this up together. We've looked at this before, right? So this is Norman Wells. This is, Alaska, you see everything. So this is in northern Canada. So, and you've seen it before because, can't get back to it. Didn't we look at some islands in the middle of a river before in this class? I think we did. So this is the idea here. Oh, it does get bigger. So this is on 3 feet of river ice. This is sitting on the Mackenzie River, frozen, February, 2 lifetimes ago for you, with water recirculating in out of this casing. This is the drill steel in the top. This is drill fluid going into this kind of universal joint that allows the drill steel to rotate, but the hose to stay static. So water's going down through here, it's going down to the bottom, then it's returning between the borehole and the drill pipe and coming out of the top. This is the hydraulic takeoff head that's rotating, and this is the mast, which is vertical in this case, that allows this thing to run up and down as you go down. So this is doing diamond drilling into rock below the riverbed of the Mackenzie River. How did I get? I guess I just did it by doing this. What's a muckluck? Okay, I'll let you Google it. It's like sorrels. You ever see sorrels? Those winter boots that you have, which are almost like overshoes. It's a First Nation or Inuit overshoe for walking through the snow that has no laces in it and so keeps your feet dry or warm. So this is the same rig, again vertical, this is the power. This actually has a solid stem auger on it, which is being wound into the ground. And so this would be perhaps in the beginning of the hole to get through the soil first before you get to hit bedrock. And then once you get into bedrock, to set it up with the rotary core that we talked about. Actually, this might be off the river. This is on the banks of the river, but drilling through permafrost in this particular case. Solid stem auger, hexagonal male coupling and female coupling. The hole here that a pin goes through, so they go together. They don't twist next to each other because there's no thread, but once you put them together, you can put a pin through the bottom of this part here into the top of this part here. And so it's solid, and so the pin can just be a solid steel pin that goes through here. And different augers to do this. This is something we haven't talked about. It's called a Krell barrel, Cold Regions Research Lab. It's in New Hampshire. They made this barrel, which is for sampling permafrost. It's just put at the bottom of the borehole, and it has really sharp stainless steel cutters, which allow permafrost to go up inside it, and then you pull it out of the ground. Not really relevant for our class, but maybe interesting. Another rotary rig. And so this is in, where's this? This is in Massachusetts. Do we have anyone from Massachusetts here? On the outskirts of Boston? I don't think we do, right? Because we did an inventory of where everyone's from. And this was a drilling project looking at a probe which had a very fine pencil-like probe on the tip to measure pressures, which was being developed to being deployed at the end of in a petroleum reservoir in the Gulf of Mexico or America, to be able to take pressures ahead of the bottom of the borehole. And so this was in clay, this is a casing, this is the drill rig on top of it. It was in winter time. I don't know why it won't go back to that. It's a bummer. What am I doing wrong? Apart from everything. And so, yeah, same as before. So this is the power takeoff for rotation. It's just being swiveled to be able to allow another piece of tube to be added to this. This gives the motive power. This is the monkey hammer. We mentioned that the split spoons are put down at the bottom of the hole, filled with drill pipe, and then driven into the ground. We might have a picture of that. So this is just lifted up into the gantry by wrapping the rope around a capstan that continues to rotate. If you put some pressure on it, then it grabs and it lifts this up. You release the pressure, it drops it down again. So you lift this up into the superstructure, and then you drop it. It has a set weight, and it goes up a set distance, so it applies a certain amount of power into the top of this tool and allows it to be driven into the ground. This is more pipe being put on. I can't really see what's going on. That was quite bright on there, actually. Don't know. This is just plain bone. All right. So the drill pipe goes into the ground here. This is just a 90-degree bend like you'd have in your house. So it goes down, but it has a side exit that comes here. So this is taking the drill fluid goes in here into the top of the drill as it's going down. It travels down the center of the pipe to the shoe, keeps it lubricated, washes the cuttings up to the back around the outside of that pipe, and then when it gets to the top, it comes out here. So this is the exiting fluid, which is carrying with it its the cuttings. So if you put a household sieve underneath here, you'll catch a whole bunch of pieces of rock, which are the size of the tip of your little finger, which you can then tell whether you're in clay or sandstone or whatever, to be able to do that. So that's very low key. That's exactly what's happening here. So drill fluid in here, down the inside of the pipe. These little pieces of string, the pipe joins, these pieces of string are put around the threads so that when you screw it up and tighten it, it seals it against the water. So the water is trapped in here as it goes down here. It doesn't leak out into the formation. So if you want to remove it, you'll take it up into the drill mast. You'll hold this portion so it doesn't move, and you'll wrench it. So you take it against the threads and unscrew it. So this would allow you to unscrew this piece by, should be grabbing it. I guess it's grabbed here against this stage, so it won't fall down the hole. You take off this coupling, or you add this coupling, and then you raise it into the mast and be able to take it off piece by piece. The mast is is taller than the longest piece of drill rod you have, because you want to be able to lift it all the way up and break the joint off at the bottom, hold it above the hole, take this piece away and store it in the rig, then bring the mast coupling down again, attach it, and then lift this the next 10 feet and do the same. So very repetitive. So this is breaking pipe, I guess, pulling it out of the hole. This is what it looks like. These are hollow stem only augers along the side. Actually, look like this one might be a hollow stem on the side. Yeah, they are. They're hollow stem, actually. I was thinking they would be solid stem. Drilling fluid that goes up on this line. This is power that turns this stage. This is under an overpass somewhere near Boston. This is the turning stage. This is where the drill fluid goes in. This tapered connection is a tapered thread so that you can undo them. So you screw them in just by turning it, and you tighten it. Can you see it? A little piece of string here to seal it, very low tech. Augers on the back of here. Same kind of, yeah, these are hollow stem augers. So this is a hollow stem auger. You have the pipe go down the middle. Obviously, you can't join these together by putting a clip across them, because then the hollow stem can't get across it. This is a cutting shoe on the bottom most hollow stem auger. You saw it as this little U-shaped thing, where this is really these little picks which cut into the soil as it turns. This looks like solid stem auger with a hexagonal connection. Yeah, okay. We talked about tricone drilling and Howard Hughes. This is a tricone bit. Perhaps you can't see it so great. What it is are 3 cones, tricones. They have an axis which goes through here, which they rotate on. That axis is fixed to the top of the bit, and you put it down to the bottom of the hole, and you just turn it and keep on turning it. So as a result of that, you can imagine that these tricones just run over like wheels at the bottom. But these tricones have little cutters on them. They're usually little buttons, like a button on a jacket, less than 1 inch across. And this is pushed so hard into the bottom of the hole that it fractures the stuff underneath them as it rolls over at the bottom of the hole. And it makes it into a piece of cutting that is then washed by fluid that comes down the middle of this, down the hole from the middle, washes across these, and washes back up this. These are the threads. They're all tapered so they can be put together quickly and undone quickly. The string that we saw would go around this just to be able to seal it. So that's what you see. Again, the string here, drill fluid. This is the monkey hammer. I call it monkey hammer. I don't know if it's a monkey. I think it's called monkey hammer. This is on the top of rod that's going into the ground. This rod would almost certainly have a split spoon on the bottom of it to sample. And then this is just a very heavy outer piece of steel with a central shaft, and it's raised up to some height and then just dropped. It's raised up just by attaching the rope at the top of this to a capstan, goes up. I guess that's it here. This is the rope that's coming down. It's attached around a capstan. If you apply a pressure to that, it will lift it up. And then when you drop the pressure, it will drop it down. And so you'll bang this into the ground until it goes a foot, typically. Count the number of blows, then disassemble it, take out the sample, bag the sample, and use the number of blows to say how competent the rock was, or soil in this case. That must be the hammer here, doing its thing. Put pressure on the capstan, lifts it up into the rigging, and then drops it. This is a drill rig in Jinan, in Shandong province. If you ever go to a Chinese restaurant and drink Qingdao beer, this is the anglicized spelling of Qingdao beer. And so this is a rig doing soil sampling in China, still used in the UK, some of these rigs are. It's just a tripod, it's a bit like cable drilling. You put the tool into the ground and you go into the ground to sample here, and as a result of that you take a sample out of the ground. Very transportable, it's just a tripod with a cable going down it. You just need a winch to be able to lift the tool and drop it and to do the sampling. Not a bit rudimentary. So you see here, this is the tool going into the ground. East side of the Rockies, near Jasper, if any of you know where that is. It burnt down a few years ago, unfortunately. Jasper, Alberta. So this is Calgary. Banff is here. Calgary Olympics were in Banff before your time, I realize. Are we out of time already? You're wrapped. You're not even looking at your computers. What the hell's going on here? I know what you're doing on your computers. Sometimes writing down stuff, but so I thought we'd go, well, good, we'll continue with this next time. So we talked a little bit about drilling methods. Next time we'll talk about sampling. So we'd like to be able to get samples out of these to say something about what's going on. Drilling is really just a way of advancing to getting to a point to be able to do sampling. So we'll talk about that last time. That was fun. Thank you for your attention.